I am pleased to welcome you to the 10th Annual Langbein Lecture. I am Ken Potter, President of the Hydrology Section of the American Geophysical Union. The Langbein Lecture was established to recognize lifetime contributions to the science of hydrology and unselfish service promoting cooperation in hydrologic research. The lecture commemorates the remarkable career of Walter Langbein, who made significant contributions on a number of fundamental problems in hydrology and geomorphology, and at the same time worked to facilitate the application of basic research results to the management of water resources. I am most pleased to introduce George Hornberger, this year's Langbein Lecturer. The range and significance of George's research contributions to hydrologic sciences have been most remarkable. I will not attempt to summarize George's prolific research record, but I would like to make some observations. In reviewing his list of publications, I was struck by the realization that almost from the beginning, George Hornberger has approached hydrologic phenomena from a totally integrated perspective. What do I mean by this? For one thing, George has made a habit of simultaneously applying physical, chemical, and biological principles to a given problem, often by forging productive research collaborations. Second, nearly all of his work has involved both field investigations as well as mathematical modeling. Third, he has worked in a wide range of environments. His main emphasis has been on flow and transport in surface and groundwater systems and across interfaces. But he's also investigated lake and coastal systems. He has worked on both natural and disturbed systems. Finally, George has applied this integrated approach to problems that are both fundamental and critical to society. George has essentially connected many of the sometimes disparate elements of hydrologic sciences: surface and groundwater, quantity and quality, modeling and field, natural and disturbed, fundamental and applied. In doing so, he has provided an ideal model for the discipline. In addition to compiling a rich research record, George has provided extraordinary service to the science community. He's been editor of Water Resources Research and currently chairs the AGU Publications Committee. He is also the North American editor of the Journal of Hydrologic Processes. He's been a stalwart contributor to the National Research Council, so much so that he was recently named as a National Associate in recognition of his extraordinary service. I should also note that he's a member of the National Academy of Engineering. Without further delay, I'm most pleased to welcome George Hornberger, this year's Langbein Lecturer.
Thank you, Ken, for such a nice introduction. I also want to express my thanks to the Langbein Selection Committee. It is indeed a great honor for me to be here. I will make one, I'll call it an acknowledgement. Alan Bradley was the Spring Program Committee Chair for Hydrology, and around about March, I was particularly busy and preoccupied and had some things going on in my life that made it even difficult for me to respond to emails. And Alan badgered me mercilessly to get my abstract together and do a title. And so I finally relented and pulled it together pretty much on the spur of the moment. And the good part of that was that I felt totally relieved that I had fulfilled my obligation to Alan. Of course, then came May, and I realized that I actually had to deliver. And so, as a fan of truth in advertising, I think I have to make some preliminary comments here while my title slide is still up. So first of all, I want to tell you what this lecture will not be. I don't intend to answer the question in the title definitively. I also don't pretend to be capable of contributing to the body of work that has gone on in the social sciences on topics along this line. For example, people like Sheila Jasanoff, a social scientist, and Jerry Ravitz, a philosopher, have written profound things about topics not totally disconnected from the title. And as I said, I don't pretend to be in their league. And finally, what I won't do is try to offer a comprehensive review of all hydrological models that have been used, that have these characteristics. There's no way that I have the breadth to even begin to think about taking on that prodigious task. So now you're all wondering what it is I am going to do. And I hope that all of you don't sneak out of the room having heard that preamble. What am I going to do? I'm going to give you sort of a personal, idiosyncratic recounting of some work that I was involved in throughout the 1980s and a good part of the 1990s. And that had to do with some work on the problem that we know commonly as acid rain. And in fact, work that I was involved in looking at assessing the impacts of atmospheric acidic deposition on catchment waters and soils. Next one, Harry. I thought that this might prove a useful slide for context. The debates that typically go on about the usefulness of policy to usefulness of mathematical models to inform policy decisions often relate to complexity and uncertainty. Whoa, thank you. And I would add, they often have to do with time constants as well, and that was part of the reason that I put that in the title to talk. So time constants don't explicitly appear here, but Bradshaw and Borchers, you'll notice acid rain they have somewhere toward the right side of this diagram, and the right side of this diagram is increasing complexity and uncertainty and scale, and a larger reliance. Well, the scientist in this room won't like the right-hand label on the bottom axis here. Weak inference, complex, untestable hypotheses. And depending upon how we interpret those words, we may in fact be more comfortable with them. On the left side, strong inference, for those of you who are not interested or not familiar with the concept of strong inference, it's one that suggests that if you can frame a scientific question as determining between two alternative hypotheses, and then you can construct a critical experiment that will eliminate one and not the other, then you are following a path of strong inference, and people have made arguments that the field of molecular biology has progressed so rapidly because that is exactly the structure that is generally followed. And for things like problems like acid rain, I think that we probably all do agree that it can be quite difficult. And what happens is that in such instances, observations of environmental phenomena are often, or perhaps always, maybe always is too strong, often interpreted with the use of mathematical models. The observations themselves are interpreted. The uncertainties can be quite large in drawing such inferences from mathematical models. And I think that it's fair to say that there is quite a bit of pessimism rampant on the applicability or the utility of such models. Certainly plenty of debate, if not skepticism. Next one. Okay, so as I said, what I'm going to do is concentrate primarily on the acid rain issue as an illustrative example. And this is just a little bit of background for those of you who perhaps didn't live through the magic era of the acid rain research in the 1980s. The impacts, or the purported impacts of acid rain, were reported in the 1960s and 1970s, mainly in Scandinavia, Canada, and the northeastern United States. The issue was called to prominence primarily by limnologists, famous people like Gene Likens pointed out that waters, there was evidence that waters were being acidified in these areas. The idea was that the acidification was taking place because sulfur in emissions, coal burning and oil burning power plants were emitting sulfate into the atmosphere, and this sulfate from the atmosphere was deposited, and sulfate was a mobile anion, so it traversed through the soils to the stream, and of course it has to be balanced. And to the extent that sulfate is balanced by an acidifying ion, hydrogen ion as an example, then surface waters would be acidified. Like many such environmental controversies, this one was a controversy. That is, people debated this. This was not just widely embraced, yes, this is happening. People disputed it. They talked about the ignorance of the impact of organic acids in mitigating effects. It was said, well, sulfate in many systems is not all that mobile. It will be absorbed by soils, by clay minerals in the soil, and so forth and so on. And so there was quite a bit of debate about just what could be said. One of the things I think that was agreed from the start was that any impacts observed would occur over a period certainly of a decade and possibly many decades to a century, depending upon characteristics. And this makes for a difficult observation problem. Right? If you want to just base it on observations, then one has to detect a trend from amidst a stochastic signal, climate variability, meteorological variability. So it's a difficult observation problem, and it's certainly a difficult forecasting problem. Next one, Harry. In the early 1980s, I wrote a proposal to the Environmental Protection Agency to develop what I termed in the proposal a model of intermediate complexity to describe the impacts of atmospheric acidic deposition on soil water and stream water. Jack Cosby had just finished his PhD at UVA at the time, and I signed Jack on as a postdoc when the EPA actually funded the project. And also Dick Wright, who's a limnologist from Norway, came on sabbatical in 1983. And so we had a team there at the University of Virginia that participated in pulling together a model of what we termed there a model of acidification of groundwater in catchments. And I have this slide up. It's a report to the EPA. When people would hear me talk about magic, they would say, oh, yeah, well, just sort of lucked out with that acronym, because you can pronounce it. But I think the picture indicates that we did actually give some forethought to constructing the acronym, and it was a tongue-in-cheek acknowledgement that, in fact, this was not going to be a very precise forecasting business. Again, because we were looking to create what we call the model of intermediate complexity, we treated the catchment as just a black box, a totally lumped model with the water going through the soil. And we envisioned running this on an annual time step because, again, of the long time constants involved. And we wanted to make sure that we could run this model easily and without taking up days and days of time on the computers of the early 1980s. Next one, Harry. I promise you I will not go into great detail about what's in the model, but for completeness, let me just try to give you my arm-waving view of the processes that we included so that you have some appreciation of exactly what we did. The basis of the model was a set of equilibrium reactions involving dissolved carbon dioxide, a solid phase of aluminum hydroxide, because aluminum is important, it's one of the acidifying ions, aluminum and base cations in the soil water, and alumina and base cations adsorbed to the soil. Some of the parameters in the model were reasonably well defined. That is, they were thermodynamic equilibrium constants, well accepted by the geochemical community. Others were what I could refer to as perhaps thermodynamic-like coefficients, so that selectivity coefficients as to how the process of ion exchange takes place in soils. It is not all that fundamentally grounded, partially fundamentally grounded. And then there were some other coefficients that in any kind of a lump model, if you have any experience with them, that have to be defined, having to do with fluxes through the reservoir and how certain processes take place. So we had a mathematical model that really wasn't all that complex. That is, we could do probably 100 years or 150-year simulation on an old IBM PC, and it would take perhaps a minute of runtime. That runs much faster now, of course. Also, of course, charge balance was involved, and when water flowed out into the stream, carbon dioxide degassed, and there was a reequilibration. But we used the model to, we could use the model to look at forecasts for pH, alkalinity, base cation concentrations. And again, the whole idea of this model is that the mobile anion sulfate would move through the system, and to the extent that there were base cations available on the soil exchange complex, these base cations, for example, calcium, would balance the sulfate. And calcium sulfate is not an acidifying compound, and so the stream would not be acidified. Once the base cations were stripped off the soil ion exchange complex, then the acidifying ions would come through and surface waters would be acidified. Next one, Harry. So we can do, with such a model, we can do some fairly simple experiments. Here is one that comes from that Environmental Science and Technology article that was noted on the previous slide. We just did a simple square wave experiment. And so if you look at the dashed line sort of starting in the middle, and you see at time 20 years, you see a decrease. That is a decrease in the pH of deposition for this slide. And you see that we keep the atmosphere, the acidic deposition turned on for, what is it, probably 20 to 100 years, something over 100 years. And then we turn it back off. And this is basically then to look at the behavior of this modeled system in terms of forecast, to look at the timescales. And what do we see? Well, the stream pH, that's the solid line on the graph, and perhaps if you are a fisheries biologist, that might be the one that's most important. Right? So it's certainly, from a resource management standpoint, the solid line might be one of the more important things that you'd want to look at in terms of a forecast. So the solid line, what do we see? We see that the stream pH declines over a matter of decades. There's a first phase where the sort of the white lines divided up into several phases that we mention in the paper, but the first portion is, of course, pre-acidification, where nothing is happening. And then the next phase, where we get this decline, is where the sulfate adsorption is still active. And so the sulfate adsorption sites on the soil complex are not saturated. So we're getting, at first, all of the sulfate coming through is balanced by base cations. There's no acidification. Then as the sulfate adsorption sites become saturated, we get more and more of the acidifying ions coming through. The pH drops. The next phase is where the sulfate adsorption is saturated, and then right out there, somewhere around 130 years or so, there's a period where we reach a new steady state, where the inputs are balanced by the outputs. The catchment has been acidified. The stream has been acidified. And then after we turn the acidification off in this experiment, it takes even longer for the sulfate to be from the system and for the base cations on the exchange complex to be replenished by mineral weathering. So that's an even slower process. So there's an asymmetry here as well. So not only does the process, the acidification process, take decades, there's an asymmetry. It takes even longer to recover once the acidification is turned off. And at least in this particular simulation, which had parameters that were appropriate for Central Virginia, we can see that this whole cycle might be looked at in terms of a century or more rather than just a decade or two. Next one, Harry. The question, of course, with any such model is, okay, that's a nice toy model. We can look at timescales, but can we really use it on real systems to make forecasts that are useful? That is, can the model be trusted? And this approach, our approach, I don't think is totally dissimilar from approaches taken by many people throughout the hydrological sciences for a whole variety of models. What did we do? Well, we calibrated the model. One of our first ventures was to calibrate it to a catchment that we monitored in Shenandoah National Park of Virginia, White Oak Run. Calibration of a model, of course, how does this, let me back up a minute. I should have told you a little bit about how this model runs and when we apply it to a real catchment. The first thing we have to know is an input sequence, and the input sequence has to be for the atmospheric deposition for, let's say, the past 150 years. How do we know that? Well, we don't have measurements. There were no NADP stations back in 1900, at least none that I'm aware of. And so we had to do a reconstruction. We did a reconstruction based on pretty good estimates of emissions from power plants. And we basically scaled present-day deposition to current. Once you have that input, it turns out that the model calibrates fairly well just to the known water chemistry, average water chemistry of a catchment present day. And it's constrained, actually, amazingly, fairly tightly, pretty tightly. That's not really the kind of test that people look for. They say, yes, but what you want to do is project outward. We want to forecast what the world is going to be in 10 or 20 years. How will it do then? Well, to a certain extent, we have some experiments that have been done. So Dick Wright and Jack Cosby applied the magic model to several manipulation experiments that were conducted in Norway, where small catchments, very small catchments, were acidified. That is, they did catchments in part of Norway that had not received acid deposition, and they basically built a roof over the catchment, small catchment, and acidified the precipitation coming in. So what the argument that Dick and Jack make is on the left-hand side, you see, well, the sulfate, the magic prediction looks pretty good in terms of the acidification measured underneath this roof catchment. On the right-hand side, you see that quite often when we do these things, not everything works out perfectly, though. And so what happened is they got the pH actually about right, but the distribution of acidity between aluminum and hydrogen ion was not right. And it's quite interesting. Let's go to the next one, Harry. That's actually this is where you see in the right panel the disagreement, if you will, between the partitioning. So what Wright and Cosby did in a series of papers, they went back and they said, well, we really need to modify magic. When we originally developed magic, we didn't account for organic acids. And organic acids are thought to be important, at least in some regions of the world where the waters are highly colored. And so they went back and they said, well, fine. They put in first a pretty simple organic acid module based on total organic carbon measurements, and then they actually went back and implemented a more thermodynamic-based approach that Charlie Driscoll had suggested. And what happens when you do this is you then get improvements, at least to the parts of the model where there was disagreement. I think that going back to, I guess, my second slide where I mentioned strong inference, this is, I think, what the people mean when they say, well, we're not really engaged in strong inference. We don't do an experiment to reject out of hand a model. What we do is we do an experiment, and if the model does not conform to the observations, we say, aha, we have to go back and modify the model. And I would contend that that's really is the way we work in the environmental sciences. And I'm not saying that there's anything wrong with it, but it's not what sort of philosophers of science refer to as strong inference. Next one, Harry. Another aspect of these kind of hydrological problems is that we are often not interested first and foremost in the behavior of a particular catchment. We would like to, the EPA, for example, was interested in making an assessment of what would happen in all of the northeastern United States or all of the middle Atlantic states. And so we also run smack into the problem of regionalization. How do we take observations from selected catchments and extend our inferences to a region? One of the ways that we explored, that we put forward actually, was rather than to take an approach where we would fit magic to data from an individual catchment, we said, well, if we have a regional survey, if we know something about the distribution of water chemistry in a region, then what we might be able to do is choose magic parameters, fit magic, to reproduce the regional distribution rather than a single catchment, and then use that, do this in a Monte Carlo framework, and then we could use that distribution of models to forecast into the future. And so we did that for, we applied this to a set of data that we had for, how many did we have? I think we wound up using 464 lakes from a 1974 survey of lakes in southernmost Norway. All right, and what you see is that we evolved a procedure where we could take thousands of Monte Carlo realizations and weight them appropriately so that we could fit the joint distribution of, I think it was something like 11 water quality variables. And so we're fitting the joint distribution in a fairly high dimensional space, an intermediate dimensional space perhaps. And we could pick, we could repeat this. And so we could use different ensembles, 1,000 run ensembles. And the dotted lines at least then give us some representation of the uncertainty in the fitting procedure itself as to how well we could do. In 1986, 180 of the lakes were resurveyed, and this then offered us another opportunity to see how we would do in a forecast mode. And basically because we calibrated to the 1974 survey, and then we could project forward to the year 1986. And what is shown here, these graphs show the change in alkalinity. The top left panel, I think the top right one is pH. And what you see is the distribution again of the change in these variables from 1974 to 1986. And sort of the trends were about right. We certainly didn't get the variance. The variance and the actual changes were larger than we saw in the measured. What was seen in the 1986 survey, interesting, was this tendency to higher pH values and lower sulfate values. There had already been a decrease in sulfate deposition throughout Norway, but also seen was about a doubling of nitrate values. And the original magic didn't even take nitrate into account. So some interesting things there as well. We took a second approach. The Environmental Protection Agency, and this I think illustrates another thing that is commonly done in application of environmental models, and that is the Environmental Protection Agency actually used in in an assessment, a regional assessment for the Northeast and for the Middle Atlantic, they elected to use 3 different models. MAGIC was one of them. The other 2, the one was ILWAS. This was a model, Integrated Lake and Watershed Acidification Study. Tetra Tech did that work. And the Enhanced Trickle-Down model, which was generated by people at the University of Iowa. And the charge to everyone was to fit each of these models to 126 catchments in the northeastern United States. We actually decided that we needed to have a fuzzy calibration procedure, and so we didn't try to fit to the exact measured values. We said, well, we're going to have a window that would represent the variance in measured water quality variables, and we basically calibrated 10 different times and at least got some crude level feeling for uncertainty in the projections. And the reason I say that this is also important, this is sometimes referred to as model structural uncertainty, because the uncertainty that we would look at within MAGIC is just within MAGIC. EPA was also interested, I think, in the uncertainty depending upon the model structure chosen. This is, I think, the more popular term now is conceptual model uncertainty. Right? And so the question then asked is, how robust are these models? Next one, Harry. The Department of, I think it was the Department of Energy, sponsored a group at Oak Ridge National Lab to do a systematic comparison of ILWAS, MAGIC, and Enhanced Trickle-Down. And this was, I think, a very creative exercise headed up by Kenny Rose, but involving several other people at Oak Ridge National Lab. And the first thing you can imagine, these models are quite different. So the ILWAS model runs on a daily time step and accounts for soil moisture, does all of the things that are near and dear to hydrologists' hearts, okay, and if looking at catchment models, and divides catchments up into subcatchments and accounts for evapotranspiration and plant uptake and all sorts of processes. Enhanced Trickle-Down, and also I think has 5 soil layers, and Enhanced Trickle-Down had 5 soil layers, and I think as well. So at any rate, the models were quite different, and they actually even represented certain processes slightly differently. So the first thing that Kenny Rose and others had to do was figure out how they could get all of the inputs into a comparable phase so that the models were being driven by inputs that would allow an objective comparison. And so I think that they did that quite admirably. And this is a graph from one of the papers published by Rose et al. Their conclusions, they applied this to 2 of the northeastern catchments. And they said that the results for forecasts of acid neutralizing capacity and sulfate were all within the uncertainty bounds of the 3 models. So that, again, the models basically produced the same answers for 2 of these catchments in the calibration set. They then extended it and said, well, let's look at how these models perform if we stress them a little differently. And so they found what their conclusions in the paper were that under moderate changes in sulfate deposition, and by moderate they meant less than about 50% change in current deposition rates, the models produced similar results on a relative scale. They were convinced that the models were robust to making forecasts of relative changes. When there were large changes in sulfate deposition, say greater than 100% change in current values, the models actually produced quite different results. So, what do we conclude from this? Well, I suppose we might conclude that, at least for forecasting trends in sulfate and acid neutralizing capacity, we might consider these models to be reasonably robust. I will say, however, you remember I mentioned the nitrogen increase in the Norwegian 1986 survey, and people have gone on and tried to include nitrogen in the models, and there was a 1995 workshop on nitrogen modeling, in which they compared a variety of different models and came to the conclusion that none of them worked very satisfactorily at all. So nitrogen is a little more difficult. Well, of course, it's much more biologically active than any of the other chemicals. Next one here. Okay, so having gone through this exercise, we might get at least to a start on the question that I had in the title of my talk, and ask a question, well, what do scientists think? So here is a quote from a paper, a 1997 paper that my friend Colin Neal wrote. And what does he say? He says, well, little trust can be placed in the predictive capacity of the current hydrochemical and environmental impact models associated with acidic deposition. Their use in determining environmental management policies may well be overemphasized, misplaced, and counterproductive. That was Colin on a good day. Okay. But let's look at the next slide, because this is, again, a quote from Colin's paper. And this occurs, it may not be in the same paragraph, but it's the immediately succeeding paragraph, if it isn't the same paragraph. And Colin says, the models serve an extremely valuable purpose of providing learning tools for examining the dynamics of water quality change, both within the framework of hydrological events and of long-term changes in catchment stores and evolving end-member compositions. So I think it's really interesting. I think that these two quotes perhaps capture a sense that quite a few scientists have. At least when I talk to scientists in the hallway, they will say such things to me. And what do they mean? They say, well, models are really good for science, within science. We like to use them because we use them to sharpen our intuition, and we use them to frame hypotheses, to move science forward. But we're not really happy with the uncertainty embodied in these models and going forward to actually make policy, not decisions, but to inform policy decisions. And it's quite interesting when some of you, at least, were in the session immediately prior to this one on the Consortium for Hydrological Sciences. And one of I guess their primary scientific aim, if I recall the slide correctly, I'll paraphrase it, I won't get it exactly right, has to do with making predictions, making hydrological predictions, and tied to water resources issues. And of course, I would maintain that some of these important issues are going to have long time constants. And so that this sort of dual personality of hydrological scientists is probably something that we should think about and find ways to explore, at least the implications of anyway. Next one. Now, the problem I've always had with saying, well, the models are good for science, but by golly, let's not ever let them outside science, is that then you ask the question, what are the alternatives? And I've never had the alternatives laid out to me very clearly in an articulate way by many people. So, and I think this quote from a paper by Ed Rastetter in 1995, and Ed was actually writing about models of global change, in particular global carbon change. But again, I think there are a whole suite of hydrological and environmental models that we could probably put under this same kind of umbrella. And what does Ed say? It says, these models are likely to remain a vital part of any evaluation of the response of changes in global climate and carbon dioxide because the alternatives are worse. It would be foolhardy to plunge blindly into the future without some attempt to evaluate the global consequence of human activities. And when we have things, when we have long time constants involved, complex processes, it's hard, at least for me, to envision how we're going to do this without some kind of use of mathematical models. Next one, Harry. So, where do I come down? By the way, these kind of debates do have or can have some important implications. And so this little title from an ES&T article from 1995, this was when the EPA was considering whether there should be changes to reduce nitrogen deposition. All right? And the Science Advisory Board for the EPA at that time basically dismissed the use of mathematical models by the EPA to help inform this decision because the approach lacked detailed biological processes. Right? And so I think I haven't seen the issue revisited, but it would not surprise me at all that if the EPA went back and incorporated detailed biological processes, that an advisory board would conclude that the uncertainties associated with these detailed biological processes were so large that these models couldn't be trusted. There is a real dichotomy. All right, skepticism about modeling notwithstanding, my own take is that the acid rain story that I just went through as an example is really a success story. Okay? I think that there is an awful lot more known about science, about the processes that from work that was stimulated by the scientific controversies attending the problem. We just learned a heck of a lot more. And furthermore, we also learned, I think, a lot better how to employ models, how to compare different models with different structures, things like this. And at least in Europe, I would argue that it's a success story with regard to actually influencing policy, because the Europeans did accept a critical loads approach to managing atmospheric deposition. And these critical loads, at least in part, were a reflection of what model predictions, various model predictions, said would be acceptable to attain a certain level. So I think that these models with long time constants that are used to analyze scenarios of future change has proved beneficial and useful. And this is my last slide. It's a quote that I took from a fairly recent National Research Council report, Our Common Journey, a Transition Towards Sustainability. It's a so-called sustainability report from the academies. Whether you like or don't like that report is not the issue. But I did want to quote this one thing. Toward the end of their report, they are talking about various methods of scenario analyses. And of course, they're not restricting it by any means to acid rain. But again, I think there are a lot of things that can fit under this umbrella. At their best, however, these methods have helped determine efforts to probe the future implications of present trends, to identify the likely obstacles to sustainability, and to illuminate alternative options for moving towards specific sustainability goals. In doing so, they have helped us to learn a bit about what a transition to sustainability might actually entail. This learning is a process through which notable progress has been made using various methods of scenario analysis. That is a surprising and optimistic finding in itself. Thank you. Okay. Does anyone have any questions? We have time. John? So I'll try to abbreviate John's question. I'm told to repeat the question, John, for the microphone. The abbreviated version of his question is, how do I see the use of models that is made in things like court cases deciding damages, where they are actually the numerical values from the models are used, and that's certainly true. This is also an issue that is, as you well know, is fraught with controversy. The whole application of scientific testimony and the admissibility and the vetting of experts by judges there have been 2 Supreme Court decisions within the last 5 years, I think, basically the Delaney decision, which reaffirmed scientific expertise. That doesn't answer your question. My take, John, is that I believe that scientists who use numerical models in presenting court cases are also using their deep knowledge of systems, and they're bringing an awful lot more scientific knowledge than just the numbers that get ground out of a numerical model to bear on a case. And so I think I'm comfortable with the use myself.
Yes, I have 2 related questions, and if you could comment, I would appreciate it. First deals with your comments on, you mentioned conceptual modeling uncertainty, where you actually choose a different model and see what the differences are. But what about the case where, say, the models are the same, the data are the same, the people are different, and they use the same information to conceptualize the problem differently? I don't know if you've done any work in this area. If you could comment on that, that would be nice. The second one is, could you comment on the utilization of analytical, semi-analytical, empirically based models versus going straight to the use of the most complicated 3-dimensional models in doing the assessment exercise?
Okay. So there were 2 questions. First, the first, I'll try to remember them. I may have to prompt you for the second one. So the first one had to do with what I will call model intercomparisons. Are model intercomparisons valuable where it's not so much conceptual model uncertainty, it's rather how various models are implemented by different groups of people? And I really do think that all of the model intercomparisons that have gone on in a whole range of areas are quite important in this area, and I think they've been quite instructive. I think that is the way to address that question, by having formal model intercomparisons where data sets are given to different groups and they are asked to run their models on these different data, and the results are compared. And I think sometimes what people find is that it's a great way to find bugs in your own model, because sometimes your conceptualization isn't what you think it is. Other times, and most times, I think that the model comparisons are quite reasonably favorable, and we learn things about how different approaches can give different answers. The second question had to do with what I think about jumping directly to the all-singing, all-dancing, 3-dimensional, include-everything model, rather than perhaps starting with simpler analytical models for at least a preliminary assessment purpose. And the way the question was phrased, you probably heard it in pretty much that way, and so it was loaded. I was directed to give the correct answer, and that's good because I agree with the answer, and that is that obviously one has to do, if one doesn't do a simple calculation first, you're completely off base. I mean, I can't imagine, for example, thinking about doing an experiment, just a simple lab experiment, and going ahead and doing it without sitting down with a pencil and paper first and trying to at least get an idea of what the bounds would be. And certainly the same thing has to be true for very complex situations. I think we probably don't make enough use of some preliminary calculations and sometimes go off on the wrong track for quite a way before we do that. So I'm a big fan of doing exactly what I think you were suggesting. Yeah, that's a very good question. Steve's question was how I resisted the temptation to go from a lumped model with an annual time step to something a little more distributed in time, certainly, and maybe even in space. And that's a great temptation, right? The temptation for scientists, I think, is always to go to finer and finer detail and represent more and more things. I think it was pretty easy for me to resist that temptation because my own belief was that if one were going to an assessment looking out 50 or 100 years, which is what our interests were, and one wanted to do that from a daily or finer time step, then you have to come to grips with how you're going to deal with meteorological changes over that time span and whether you're going to account for secular changes in climate. And you have a whole range of issues. And furthermore, it's not very hard to show that if you have an actual signal that's noisy because of stochastic variations in precipitation, it's not always the easiest thing to pull the trend out of that, even if you have a fairly long data record. The noise confounds it. So it was easy for me to resist that because of the overall aim of the study. Now, the people at Tetra Tech, what they were looking at, and the reason they went to a daily time step model, they started out looking at two lakes in Woods and Panther Lakes in New York, where they were trying to simulate changes on a daily basis, and so it made perfect sense for them to be in that area. That also made it harder for them to make projections 100 years in the future. They had a lot more trouble with instabilities in their model than we did. Other questions or comments? So the question is, what's my view on the role of science in bringing information to policymakers, given that if we include a full range of uncertainty, there may be a likelihood that the information will be dismissed out of hand because the uncertainty is too large. That's been suggested, by the way, that exactly that will happen. Dan Sarowitz and I guess it was Roger Pilkey Jr. wrote an article in GeoTimes about 2 years ago, and they basically made that point. Having said that, it's certainly incumbent upon us to, I think, reveal, if you will, the range of uncertainty. I think we may be surprised. That is, I think that decision makers, we may find, are a lot more able to deal with information given uncertainty bounds, if you will, than we think. When I chaired the water cycle study group that produced the water cycle initiative, I remember we had a meeting and we were talking with, I can't remember his name, but at any rate, he was with basically a Western water person whose role was trying to figure out how to operate dams along the Colorado. And we were probing him, the committee, and saying, well, would projections of climate change for 50 years in the future be of any use to you given large uncertainties? And his answer was yes. He said, absolutely. I would really, if you can give them to me, of course I'd like them with small uncertainty bounds, but they would be very useful for me in trying to figure out what the risks I would be taking in not doing one action or another. So we may be surprised, but I do think that we have to continue to strive to bring the uncertainty representations within models to the fore. We simply have to be honest about that. Okay, so let's see. John's question was if I were running the National Science Foundation and wanted to make an investment in science, would I prefer to reduce the bias in model forecasts or reduce the variance? I don't have a simple answer to that, John. And I tried to repeat your question as slowly as I could. Does anyone else want to answer that question? We'd obviously like to do both, and I don't know how we would make a value judgment on one versus the other. Okay, so to paraphrase the question part of it, Ignacio asks, sorry, Raphael. Incoming president, Raphael Bras. Sorry, I saw Ignacio sitting over here somewhere. Asks or points out that social science or economic forecasts, I think, are much, much more uncertain than anything we do, and yet these are accepted. And some science projections are accepted and decisions taken, giving the example of the Montreal Protocol. I think you're exactly right, Raphael. It's not the answer, though, why people are more willing to act on economic projections than they are on science projections. I would say it's probably those two are not totally unlinked. And therefore, for example, if we take projections of doubling of CO2 and the potential impacts and say, well, all right, why don't we have a policy of reducing CO2 emissions? And that's become very difficult to implement. And part of that is the very large cost. The Montreal Protocol is interesting enough because the technology had already been developed to replace Freon. And people were willing to go in that direction. So I think that these are not unlinked from economic issues. The other thing is that I think that it is fair to say that we have this sense that science is certainly less trusted now than it was 50 years ago. And part of it is that people see that scientists have these great disagreements over very important social issues. And they see the disagreement, and there is a distrust. So I suppose if Greenspan had a counterpart who had equal weight and came up and disagreed, of course we all read the editorials in the papers that do disagree sometimes with Greenspan. It's a good question. I don't think that's totally unlinked with economics, though.
On behalf of the American Geophysical Union, I'd like to present George with a statement of his contribution here in the Langbein lecture, and I want to thank him for a thought-provoking, entertaining lecture, and I want to thank you for your very interesting questions. I think they leave us a lot to chew on as we eat our lunch, so have a good meeting. Thank you.